In this lesson, we're going to be graphing y equals tangent x and y equals cotangent x. Let's start first by graphing them on the calculator. So again, make sure you're in radian mode. Let's go to zoom. Remember, we're going to graph a trig function. Let's go to zoom 7. Press enter. Notice how this graph is also periodic or cyclical. It has its own cycles as well. So this is part of one of the periods, or part of one of the graphs of the tangent. Okay, so right here we can see that the graph starts from way down here, negative infinity, and it continues up to positive infinity. Okay, what we see here is that we probably have vertical asymptotes that aren't showing up on the graph. It appears that I probably have a vertical asymptote right here at x equals negative pi over 2. So it appears that if I were to kind of dash in a vertical asymptote right here, that the graph is approaching that vertical asymptote up here at infinity. And then if I were to dash in the vertical asymptote to continue down here to negative infinity, that the branch of this next part of the graph is approaching that vertical asymptote on the right-hand side of it. So it looks like we have a bunch of vertical asymptotes in here that break up this graph. So when we look at the repetition of what's going on, we can really just focus on one of these pieces here. So that would be considered one period of the tangent graph right there. So we're going to graph these by hand and really dig in and look at a little bit more of what's going on. As a reminder, the zoom 7 trig window, I said that this is probably negative pi over 2. If you hit the window key, again, as a reminder that this is almost going to negative 2 pi to positive 2 pi, and the scale is what tells us what the tick marks are. So if you take the value of pi and divide it by 2, you're going to get this number right here. So I knew that the tick marks were counting off by pi over 2 increments. Let's take a look at the cotangent graph. Well, cotangent, again, we don't have that key in our calculator, so what I'm going to do is I'm going to change that. Oh, wrong key. Let me go back to y equals. I'm going to get a fraction bar. And I'm going to graph cotangent by typing in 1 divided by tangent because of the reciprocal properties. It has the same basic shape, it's just kind of reflected. If we just choose one of these pieces right here, I can see that maybe this piece, if I choose it, that we probably have a vertical asymptote at x equals 0 because the graph of this cotangent function is going to positive infinity, getting closer and closer to x equals 0. And then likewise right here at x equals pi, because this is pi over 2 and another pi over 2, at x equals pi, we probably have another vertical asymptote occurring right there. That creates the division with these graphs. And we'll see that more clearly when we go to plot these two trig functions by hand. So that's what we'll do next. Okay, notice that I have the same t-charts like I did for y equals sine x and y equals cosine x. The same t-charts in that my angles that I'm going to be looking at go from negative pi up to 0 and then up to 2 pi. I felt like it was easy to graph these trig functions if we counted off by increments of pi over 4. That doesn't mean that we couldn't include some of the pi over 6 angles that are on the unit circle. These are just lend themselves to nice numbers over here that make the graphing a little bit easier. All right, so we're going to find our unit circle. We're going to populate this column. Remember, tangent means the y coordinates divided by the x coordinates. So let's start at negative pi. So at negative pi, we're at this ordered pair. We're going to take the y coordinate 0 and divide it by the x coordinate negative 1. So 0 divided by negative 1, when 0 is on top of a fraction, it's going to be 0. As long as you don't have 0 over 0, then that's a whole different situation. But we won't get that. At negative 3 pi over 4, I'm right here. Negative 3 pi over 4, again, is coterminal with 5 pi over 4. So let's take the y coordinate and divide it by the x coordinate. When you divide these two, you're going to get positive 1. Let's go to negative pi over 2. Negative 1 over 0. Well, that's not 0, that's undefined. which that means that's going to give us a vertical asymptote on the graph of tangent. All right, negative pi over 4 is here. Y divided by x, they're opposites, so that's going to divide into a negative 1. We're at 0 now in our chart, so y divided by x is just 0, and we'll continue around until we get to 2 pi, populating this column. So at pi over 4, my x and y coordinates are the same, and when you divide those, you get 1. At pi over 2, you're going to have a 0 in the denominator, so that is undefined, and again, we're going to have another vertical asymptote. 3 pi over 4, we get negative 1. At pi, we're going to get 0. 5 pi over 4, we get positive 1. 3 pi over 2, we get negative 1 over 0. Undefined, we have another vertical asymptote. So notice that we have a lot of vertical asymptotes, and if I were to extend this T-chart by including more angles, you know, in either direction, I'm just going to have vertical asymptotes keep reappearing. 7 pi over 4 is negative 1, and at 2 pi, we're at 0. All right, I didn't leave myself enough room here. Perhaps I should have done a horizontal table, so we'll do the graph in this space right here. Okay, again, looking at what I have in my T-chart, I go from negative pi to 2 pi along the x's. Perhaps I should have moved that over a little bit more, but that's okay. All right, so we've got negative pi here. Perhaps this is pi, and then maybe 2 pi. Negative pi over 2. And then the additional tick marks for the fourths. 2, etc. 3 pi over 2 here, and the additional tick marks in between like we did for sine and cosine. All right, coming up here, negative pi plots with the 0. Oh, let me back up. So let's look at the values down the tangent column down here, down the y column. It looks like I go as low as negative 1 and as high as 0. And that's just because I've restricted myself to certain angles here. Those numbers would differ, but I'm just going to go ahead and put positive 1 here and negative 1 here. All right, now plotting. Negative pi 0. Negative 3 pi over 4 goes up to 1, so that would be here. I'd plot this point. Negative pi over 2 gives us a vertical asymptote, so we're going to dash that in. It doesn't dash in on the calculator, but we can do that certainly here. All right, let's investigate this behavior over here. What if I were to choose an angle that's close to negative pi over 2 and divide the y by the x? Well, I'm going to get a value larger than 1, so it might plot right here. The closer I pull into x equals negative pi over 2 from the left side of negative pi over 2 over here, and I take the y coordinate at that angle and divide by x, the larger that answer is going to become. So we can see the trend of these points, if we connect them, suggests that the graph approaches positive infinity without ever touching that vertical asymptote. It can't. All right, so now we're going to concentrate angle values that are greater than negative pi over 2. So negative pi over 4 plots as negative 1. So now I'm down here. All right, and where am I at now? 0, 0. And then I'm at pi over 4 and 1. So pi over 4 is here, and I'm here. Pi over 2, I have another vertical asymptote, so I guess I better dash that in. I see I have a vertical asymptote again at 3 pi over 2. I'll go ahead and take care of dashing that in as well. All right, so let's concentrate our attention right here on what's going on and see if we can kind of complete this graph right here between these two consecutive vertical asymptotes. So the point suggests that the graph might come up like this. The closer I get to pi over 2 from the left of it, the higher the y value, or the tangent value, or the y value on the graph. So you want to go ahead and be mindful of drawing the graph to continue upward and put an arrow on it. So I'm approaching positive infinity, but I'll never cross over x equals pi over 2. So what's happening down here, because we need to complete the graph? Well, the graph is going to leave this point, and it's going to actually kind of bend this way, collect that point. The closer I get to negative pi over 2 from the right of so here's negative pi over 2, here's the right of it. But the closer I get to negative pi over 2, somewhere in this area, these tangent values are smaller. So the graph goes down like that. And this looks very similar to what we graphed on the calculator. All right, what's happening between these next two consecutive asymptotes at pi over 2 and 3 pi over 2? Well, let's plot some more points. 3 pi over 4 would be here, and I'm going to plot at negative 1. Pi gets a y-coordinate of 0. 5 pi over 4, which is right here, gets a coordinate of 1. So again, the same pattern. So let's complete this part of the graph. The way it bends and turns, kind of pay attention to the concavity, if you will. Looks like this is just going to keep repeating itself. All right, then over here we have points from 3 pi over 2 up to 2 pi. So 7 pi over 4 would be right here is at negative 1 and 2 pi is at 0. All right. So I've kind of cut off half of one period over here, the bottom half, and cut off the other half of the period over here to the right of 2 pi just because of my table values that I have, my angles. But I could complete it if I wanted to, and I think I will. So what's this going to look like? Well, I'll leave this x-intercept and come and bend up this way. So can we predict what this next vertical asymptote will be? And that's going to be part of our work in graphing tangent functions with changes. So can we label this tick mark? Well, let's look for some patterns. The first positive vertical asymptote occurs at x equals 1 pi over 2. Then I'm at x equals 3 pi over 2 for the next vertical asymptote. I'm predicting that this vertical asymptote would be at x equals 5 pi over 2. Makes sense. And then I would predict the next vertical asymptote to the right of x equals 5 pi over 2 would probably be at x 7 pi over 2, x equals 7 pi over 2. So the horizontal distance between two consecutive vertical asymptotes, this distance, if you were to subtract 5 pi over 2 and 3 pi over 2, would be a pi. So the horizontal distance here is a pi. Let's confirm here. What's the horizontal distance between x equals pi over 2 and x equals 3 pi over 2? Well, 3 pi over 2 minus 1 pi over 2 is also 2 pi over 2, or pi. Let's just confirm here. What's the horizontal distance between these two vertical asymptotes? Well, I got a half pi here and a half pi on the other side of the y-axis, so that does combine and give me a pi. I think the period, unlike sine and cosine, is pi. Remember, sine and cosine's period was 2 pi, but for tangent, it's just pi. I could complete this part of the graph here, show that it goes downward. Okay, if I made a prediction over here as to what I think the next vertical asymptote would be, well, if this is negative 1 pi over 2, I bet this vertical asymptote is going to occur at x equals negative 3 pi over 2. We could also confirm using our unit circle. Let's think about negative 3 pi over 2. Negative 3 pi over 2 would put us up here at pi over 2, and y over x would give us a vertical asymptote. All right, so there's patterns that we can look for. All right, the requested information for tangent and cotangent is going to look a little different than sine and cosine because the graphs are different. I'm going to tackle answering these questions down here for this graph. So I'm going to start with range because that'll be the easiest. The range of tangent, unlike sine and cosine that goes from negative 1 to 1, the range for tangent is going to go from negative infinity up to positive infinity. So if you kind of just ignore everything except for one cycle, and just concentrate our attention on this part of the graph right here, the range is negative infinity to positive infinity. All right, well, what's the period? Well, visually, I can see that the period is the horizontal distance between consecutive asymptotes. All those differences are the same. They're all pi. So when we go to transform tangent and cotangent graphs, we have a new formula to calculate the period. Instead of 2 pi over b, we're going to use pi over b. Pi, because pi is the period for the parent function. Now on sine and cosine, we had 2 pi over b, but that's just because sine and cosine's parent function's period is 2 pi. All right, we're asked to state all the vertical asymptotes. Well, there's going to be an infinite number of vertical asymptotes, so I could generate a list. and use a dot, dot, dot to suggest a pattern. So all the vertical asymptotes occur at x equals. Remember, a vertical asymptote has to be reported as x equals. So x equals what? Well, what I see here is negative 3 pi over 2. I see negative pi over 2, etc. All right, and this is fine, and we can do comma, dot, 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 and then on this side I would do comma, and then I might move this equal sign and put a dot, dot, dot to the left of x equals negative 3 pi over 2. Without the dot, dot, dots, okay, someone might think that these are the only vertical asymptotes. All right, so the vertical asymptotes are of the form always x equals. You can generate like a list and then use your dot, dot, dots on either end. Typically, we take all of this and condense it into a vertical asymptote statement, meaning this. Instead of writing this whole pattern right here, what we can do is we can come up here and choose one of the vertical asymptotes, in here. Common practice usually has us choose a vertical asymptote that's, if it's not falling on the y-axis, the first positive one. So if I said all my vertical asymptotes are x equals pi over 2, well, what is going to be the next vertical asymptote to the right or even to the left of positive pi over 2? Well, that distance is pi. So I could say, okay, vertical asymptotes for the tangent graph occur at pi over 2, or this could be negative pi over 2. It could have been any one of these, plus a pi difference. Now I'm going to leave a little gap here because I'm going to put something here. Well, if I wrote this statement, I'm just really talking about, if I figured this out, one vertical asymptote, but I want an infinite number. So I'm going to put an n here to multiply by pi. I'm going to put a comma, and I'm going to put where n is any integer. And think about what integers are. Your negative whole numbers, 0, your whole numbers. So let's just try this. Let's say n is any integer. Let's say n is 0. Well, then I would just have pi over 2. Is pi over 2 in my list? Yep. What if I let n be positive 1? Well, if n is positive 1, then I would take pi over 2 and add pi. Get a common denominator. That would give you 3 pi over 2. What if n was the integer 2? I'm adding pi over 2 plus 2 whole pi. If you did the math, you're going to get 5 pi over 2. So it looks like this expression that condenses all of these vertical asymptotes is accurate. Let's try a negative integer. Okay, what if n is negative 1? Well, then I'm going to have pi over 2 minus pi. Well, a half pi minus a whole pi gives us negative pi over 2. Is it in our list? Yep, we're checking. What if n is negative 2? Well, then we're going to have pi over 2 minus 2 pi. If you did the math on that, you get negative 3 pi over 2, which is also present in our list. So this is the way you typically are going to see vertical asymptotes written when there's an infinite number of them. It just condenses this list into a nice expression. All right, let's talk about the domain. So what's the domain of this function? Well, the domain are all the x's except for where you have those x values of vertical asymptotes. So for our domain, it's not all real numbers. It's every number except for these vertical asymptotes. Okay, the easy way for us to record the domain is to say all real numbers except. And then I'm going to do all real numbers except wherever I have vertical asymptotes. So I'm going to say all real numbers except for where x equals pi over 2 plus n pi, where n is any integer. I won't write down where n is any integer because I already have it recorded here. And once I have it recorded here, I know that that's what that n means up here. So that's easy, domain, once you get the vertical asymptotes. Because then you can just say all reals except. All right, let's take a look at building our cotangent table and seeing how the graphs compare. Even though we already did it on the calculator, it's good to have it also recording on our notes. All right, cotangent, remember, is going to be x over y. All right, so let's go to negative pi. Here's negative pi. x over y? Well, if I put x over y, I'm going to get a vertical asymptote that's undefined, which that means I'm going to have a vertical asymptote. So my vertical asymptotes are different than what, for cotangent, different than they were from tangent. They're just shifted. All right, let's go ahead and, if you're comfortable populating this column, turn the video off, do so, and then you can turn it back on. Negative pi over 2 is 0 over negative 1, so that's just 0. Negative pi over 4. At 0, I'm going to have another undefined. So that's my next vertical asymptote. Pi over 4. And if I'm at pi, it's going to be another undefined. Five pi over 4 is 1. 3 pi over 2 is 0. I think that's negative 1. And back to 2 pi would give us undefined. Okay. Go ahead and draw the graph. I'll scale it the same way. It's half pi, and then we need those tick marks in between. I'll go high as 1 and as low as negative 1. Okay, I'm going to go ahead and dash in all the vertical asymptotes. So at negative pi, I have a vertical asymptote, which was different over here because I had an x-intercept on tangent. Then I have a vertical asymptote at x equals 0. All the integer multiples of pi. This is it's easy to predict that the next vertical asymptote would be at 3 pi, then 4 pi, as well as back to the left, negative 2 pi, negative 3 pi, etc. All right, does the cotangent graph look like this as far as the way the graphs are put in between consecutive asymptotes? No, we saw that on the calculator, but let's let our points determine that too. All right, negative 3 pi over 4 is here is positive 1. And negative pi over 2 is 0. Negative pi over 4 is negative 1. Negative pi over 4 here is negative 1. So based on what we saw over here, we know that we're going to connect these points, and the graph's going to have a little bit different kind of bend to it. It starts kind of, it's kind of reflective, I guess, if you want to think about it that way, from these branches. All right, I'm at x equals 0. Pi over 4 is 1. Pi over 2 is 0, and 3 pi over 4 is negative 1. Kind of look at the way the concavity kind of is flowing. And I'm past pi, so 5 pi over 4 is up here. X-intercept here. And then at 7 pi over 4, I'm at negative 1. I got a little bit too close to that vertical asymptote. I'm not touching it, just the way I drew it. And then that's all I have. So I can kind of see predict what the next, graphs would look like on either side of these. All right, range is going to be the easiest, negative infinity to positive infinity. The period, well, how long does it take before the graph starts to repeat and we have another branch? Well, that horizontal distance is pi. And again, the formula we'll be using for tangent and cotangent will be pi divided by the b value in our equation when we go to transform. Remember, sine and cosine is the formula 2 pi over b. All right, vertical asymptotes. Again, if you want, you can just start generating a list. You can go ... comma. I see one at negative pi. I see one, don't forget about the one at 0. Can't make a jump from negative pi to positive pi. 2 pi, and then ... We typically don't record our asymptotes like that as a list. We think about an expression that would condense this. So vertical asymptotes are at x equals, All right, over here we started with the first positive vertical asymptote. Well, the first positive one would be pi, but typically we're going to start with the 0 vertical asymptote. So 0 plus, and then we just multiply n by the distance between consecutive asymptotes, which that's the period. Do I have to write it that way? No. Could I write it as x equals n pi? Yes, that's typically the way you'll see it. Again, where n is any integer. Some textbooks will use k to represent the integer. Some use n, just depends. All right, or what if I wanted to start at positive pi? Sure. Just choose one from this list, but know that you're always going to add an integer multiple of pi. It's just more common practice to state the vertical asymptotes. This is the more condensed version as n pi. I could have done 2 pi plus n pi. Didn't matter. Just like over here, I could have started at negative pi over 2 and added n pi, or negative 3 pi over 2 and added n pi. Doesn't matter. And then the domain becomes easy. The domain is going to be every other value except for these. So sometimes we abbreviate and we say all reals except. So if you don't want to write all real numbers except and just do ARE, that's important, the equations of the vertical asymptotes. All right, so we've really dug into the parent functions for y equals tangent of x and y equals cotangent of x, and we've kind of explored some of the more common questions that will be asked regarding these types of functions. So in the next videos, we'll be looking at transforming both tangent and cotangent.